Welcome to videos on filters. So in this video we shall discuss the analysis of analog filters. The reference for this video is taken from Microelectronic Circuits by Sedra and Smith. So let us see the introduction of a filter. So a filter is a two-port network, has got input port where the input voltage is applied and the output voltage is taken at the output port. Uh, TFS is the transfer function of the filter circuit given by the Laplace of output divided by the Laplace of the input voltage. So we can obtain the magnitude of the transfer function. The magnitude of that can be the t of j omega, and the phase angle is e power j phi of omega. And we can also write the gain in terms of 20 log of the magnitude, which is expressed in terms of dBs. And we can also specify the attenuation, which is 1 over the gain. So attenuation is given by actually 1 over g of omega, which is exactly 1 over of 20 log t of j omega. Now since it is 1 over, it can be written as minus 20 log of the magnitude of the transfer function in terms of dB now. So these are the ideal transmission characteristics of various filters. Now we know that on the x-axis we have the frequency in terms of radian per second, and on the y-axis we have the transmission magnitude. So the first one is a low pass filter. So we have the ideal transfer characteristics or transmission characteristics. We're going to pass the signal without any attenuation till a frequency which is called as omega p. So this p stands for the passband edge. So from DC to the passband edge, so it will want to pass a signal. Anything after omega p, it should not allow the signal. Now this is stop band. So similarly for high pass filter, any frequencies above omega p will be the pass band. So from DC to omega p, it is the stop band. So similar to that, okay, we have this band pass filter. So where it will going to pass the signal between two uh, edge frequencies, which is omega p1 and omega p2. Frequencies from 0 to omega p1 will be blocked here, and frequencies after omega p2 will also be blocked. The signals between omega p1 and omega p2 will be uh, lying in the pass band. Similar to that, we have the opposite of this band pass filter, which is a band stop filter, which also has got two stop frequencies, omega s1 and omega s2. So where we want to pass a signal from this 0 to omega s1 and omega s2 onwards, also we're going to pass the signal. So it will going to block the signal between omega s1 and omega s2. So these are the ideal characteristics of the filters. But we know that that is idealness. Typical frequency response of a low pass filter looks like this. You can see now the ideal filter was supposed to be like this. Now this should be 1 and it should block anything after omega p. But when we actually see the typical filter, so the magnitude is not, this is actually in terms of, this is specified in terms of attenuation. So this was in terms of gain here. So now you can see this is attenuation is 0 means, so we are passing the entire signal. So the ideally the attenuation, the transfer characteristics should have been 0 dB till omega p, and it should come down here. After omega p, it should be maximum attenuation. This 0 is the frequency, and the attenuation will be minus infinity. That will be very large here, and you can see now. So here we have some variation within the passband. The passband magnitude is not. It will certainly have some attenuation. So we have frequencies not only omega p. We're going to have omega p, omega s. So this omega p stands for the passband edge frequency, which is omega p, and we have this two more parameters, that is a max and a min, and we have one more frequency which is omega s. This Amax stands for the maximum allowed variation in the passband. So ideally speaking, there should not be any variation in the passband, but typically we're going to have some variations in the passband. So this A max indicates what is the maximum allowed variation within the passband, and omega s happens to be the edge of the stop band. This is the stop band edge, and this A min, so which is minimum required stop band attenuation. So we know that the magnitude should be 0 in the stop band, but you cannot achieve that 0 magnitude over here. So we are supposed to guarantee a minimum of A minimum attenuation, so in the in the stop band. So this indicates A minimum indicates the minimum required stop band attenuation should be A min. There is a maximum allowed variation in the passband, and there should be minimum required stop band attenuation in the stop band. So we have A max in passband, we have A min in the stop band. So we have two more frequencies, that is passband edge and this is the stop band edge. So this is a filter transfer function. So filter transfer function in the polynomial form can be written as the poles and zeros. So the numerator indicates the zeros and the denominator indicates the poles over here. So upon factorizing, we can write the same transfer function in the form of pole 0. So where we have the poles and zeros being indicated in terms of P1 and P2. Now this is a all pole filter, which is a fifth order. So I'm not surprised to see what is this all pole filter. As you can see in the previous transfer function, we said that this is a pole zero form. Assume that this transfer function doesn't have any zeros. So all the, of course, any zeros means there are no finite zeros. All the zeros at infinity. A filter which doesn't have finite zeros is called as all pole filter. It has got only finite poles. So here you can see there are 5 poles. All the 5 poles are finite, whereas the zeros are at infinity. As you can see here, this is the S-plane representation of those 5 poles. So we have one pole over here, the other pole is here and its conjugate is here, and we have the fourth pole and its conjugate is here. So this is the location of 5 poles and there are no zeros. So 5 zeros are at infinity. All the zeros are at infinity. So that's why this is not having, this is not meeting this 0 over here. So this is not touching this x-axis. As you can see in the previous transfer function, you can see this is touching the x-axis, this is also touching x-axis. Whenever you have the plot touching x-axis, this corresponds to 2 zeros. So this corresponds to 2 zeros. Now here you can see, so there are actually four, a minimum of 4 finite zeros are there, and this is a 0 corresponding to infinity. So we can say that this transfer function has got minimum 4 finite zeros for this transfer function, whereas for this transfer function, since it is not touching x-axis, there are no zeros which are at finite position. All the zeros are at infinity. So that's why this is called as all pole filter. In the coming video, we shall see a few more examples of low pass filter having 2 zeros, 1 zero, or different combinations. So let us see what is this Butterworth filter. So Butterworth filter approximation is named after S. Butterworth, a British engineer who in 1930 was among the first to employ. So in 1930 itself, this S. Butterworth, who is a British engineer, actually employed it for a filter application. So this filter exhibits a monotonically decreasing transmission with all transmission zeros at omega equal to infinity. So thus making the Butterworth filter as a all pole filter. So as you can see here, this Butterworth filter has got all its zeros at infinity. So this makes the Butterworth filters as an all pole filter. This is what is the frequency response of a Butterworth filter. As you can see, it is not touching the x-axis, so this is an all-pole filter, and you can surprisingly see this is the Butterworth filter response for a low-pass filter. So at passband edge, so we have a magnitude in terms of attenuation as 1 over under root of 1 plus epsilon square. So this is at omega p. So it has got a magnitude of 1 here at BC, and it is keep on reducing. This is monotonically reducing as the frequency increases. Uh, just have a look at the magnitude function of nth order Butterworth low pass filter with a passband edge as omega p is given by. Now we are looking at the magnitude transfer function of the nth order filter, which is only the magnitude is given by 1 over under root of 1 plus epsilon square multiplied by omega p to the power 2n. So this is the expression for the magnitude of a Butterworth filter of nth order. Now this is for a low pass filter. At omega is equal to omega p, so we are substituting this omega is equal to omega p, that is at the edge of the passband. The magnitude of the filter is given by 1 over under root of 1 plus zeta square, because when you substitute omega is equal to omega p, this will become 1. 1 to the power anything is 1. So that's why this will be under root of 1 plus epsilon square. So that's what is shown in the previous graph. At the edge of this passband edge, the magnitude is given by 1 over under root of 1 plus epsilon square. So that's what we have. The parameter epsilon determines the maximum variation in the passband transmission. So as we saw in the previous example, transfer characteristics, you might have seen that. So this is what is Amax. So this Amax, the maximum allowed variation in the passband is decided by this epsilon. So that's what is written here. The parameter epsilon determines the maximum variation in the passband transmission, that is Amax. So Amax can be written as, so this is what is the gain. Suppose if you want to write the attenuation, it is 1 over this. So 1 over this happens to be under root of 1 plus zeta square. The dB representation of this happens to be A max is equal to 20 log of under root of 1 plus epsilon square. So of course we can also write conversely, for a given A max we can actually determine the value of epsilon to achieve that A max. So here in this expression, for the given value of epsilon, we are trying to find what is Amax. In this expression, to obtain the required Amax, what should be the value of epsilon? We can also estimate what is the value of epsilon for a given attenuation, for a given maximum attenuation. Now you can see the frequency response of a low pass filter for different order of the filter. As you can see here, as the value of n, which is the order of the filter, varies, so this is the frequency response for the first order filter. As you can see here, this is going here. This is the first order filter. This is n is equal to 1. This is for n equal to 2. Just see here, the flatness is keep on increasing as you are increasing the order of the filter. And it is also surprising to see all of them will meet at this point. This is on the x-axis we have the ratio of omega by omega p. So where omega by omega p is equal to 1 here, you can see the magnitude is 0.707 of the maximum. So this point is exactly correspond to 3 dB. So as the value of n changes, the cutoff frequency will not change. Only thing is that flatness over which it is flat. So the maximally flat response will be possible if the value of n is more and more. This is the response is flat only till this point if the value of n is 1. If the value of n is 10 here, you can see the flatness is more here. So in order to have a maximally flat response, so it is always necessary to go for higher order of the filter, where we can have a response which is close to an ideal response. Ideal response happens to be flat till this point and it is coming down to this 0. So now you can see the order of n is equal to 10 has got almost close to the ideal response, because it is flat till this point and it is coming down here.